record on computer. Okay. So what's 3.2 about? So 3.2 covers a lot of things: differentiability, numerical derivatives, and the alternative definition of the derivative. It's 9 pages of notes, a lot of stuff. No way, even when we're doing in-person classes, no way did I ever do this one day. Usually this over 3 days. So I will cover the first 2 pages. I'll probably do up to page 5 in the video this afternoon. And then when we come back on Monday, I'll recap some of the stuff, and then we'll probably go up to maybe page 7. We'll do pages 6 and 7 together, and then pages 8 and 9 will be done over a video due for homework on Wednesday. But you can see that we are going to talk about differentiability today. You'll see that down here we'll have some other examples and some other things we'll do. I'll kind of recap all this stuff before I end the lesson. Or do a quick preview. That's what I meant to say. Okay. So differentiability, what does differentiability mean? It's the ability to take the derivative. So just break down the words. You're able to find the derivative. Now, what does it mean to, like, how would you not be able to find the derivative when that happens? When that happens, f of x is not differentiable. When the left-hand derivative is not equal to the right-hand derivative, you're unable to take the derivative. So in example 8 of the 3-1 notes, we had a piecewise function. I just recapped it with you guys. And we saw that, oh, when the left-hand derivative was one value, the right-hand derivative was a different value, the derivative won't exist there. So we showed that derivative was not differential at x equals 1 because LHD is not equal to RHD. But when they do equal each other, then it is differentiable. So let's continue that discussion for example 1 down below. Now, example 1, you're being asked to determine if this function here is differential at x equals 0. So it's a piecewise function, very simple piecewise function. Y equals -1 and y equals 1. So if y equals 1 when x is greater than or equal to 0, so equals 0, just that. Over here, just that y equals -1 when x is less than 0. And not included there, right? Not included. Now remember, we did have this from the previous unit. We saw something kind of similar. So this piecewise function is kind of similar to what we did a while ago. Just something to take note of, but doesn't really impact how we go about solving this problem. And I'll tell you right now, actually, I'll tell you what the answer is. The answer for this is no. It's going to be no. And I'll explain how I knew that so quickly on the second page. But let's prove it first. The way to prove it is, will the LHD equal to RHD? That's what we have to prove. Now, before we do that, some people might think, oh, well, the slope to the left of x equals 0 is 0. The slope to the right of x equals 0 is 0. So I guess they would be the same derivatives, and it is differentiable. But it's not truly find the left and right-hand derivative at x equals 0. All you're just telling me is that, oh, to the right is 0, the slope is 0, to the left is 0, the slope is 0. But we actually have to kind of go through this process by brute force to prove that there are actually different left and right-hand derivatives. So we use our definition of a derivative, but for RHD, again, right-hand derivative called RHD, left-hand derivative called LHD. To do the RHD, you got to take the limit as h approaches 0 from the right side of f of 0 plus h minus f of 0 over h. And just give you guys a heads up, things will get a tad bit abstract. So, just be patient. If you have any questions, let me know. I'm going to try to give you guys as much concrete nature to this as much as I can, but there is a bit of abstractness that we can't really avoid. But this is pretty straightforward. We know this, right? We're at x equals 0, plug in 0 for a, and then we have to evaluate this. F of 0 is easy. I know f of 0 is 1 because I see it right here, and duh, when x equals 0, it's 1. Now f of 0 plus h, be careful here. H is approaching 0 from the right side. H is actually positive. It's not negative. It's actually positive because it's approaching 0 from the right side. So for example, h could roughly be maybe 0.001, right? That's close to 0. It's positive. Well, if I plug in 0 plus 0.001, when h is positive, like I'm doing like 0.001, I'm still plugging into this over here. So it's still going to be 1. Again, this limit as h approaches 0 from the right side. Well, what's 1 minus 1? 0. You have 0 over h. Then you have the limit, again, as h approaches 0 from the right side. Now, this is the weird part, too. Another weird part. You're tempted just to plug in 0 for h and say, well, then I got 0 over 0. That's an determinant. So we have a problem. Remember, h does not equal 0 for a limit. It's approach, right? It's approach. Again, h could be
Sir, you cut out for a sec.
Oh, yes. I'll just recap what I just did for the last couple steps.
Sorry.
No. I hope that didn't impact the recording. So again, f of 0 is 1. That's obvious because x equals 0 is 1. F of 0 plus h is also 1 because remember, we're approaching h from the right side of 0. The right side is 0, like h could be like 0.001. So if I plug that into here, yeah, that's going to still be 1 because I'm plugging into x is greater than or equal to 0. And the y value there is 1. Now, when I evaluate this limit, I get 1 minus 1 to 0, 0 over h. Now, someone might plug in 0 for h and say, well, 0 over 0 is indeterminate. But here's the thing. H is a super small number. This is like saying 0 over a super small number. 0 divided by anything is always what? 0. So essentially, this is just 0. So the right-hand derivative is 0. Also, if you were to draw a tangent line, like starting at x equals 0 and somewhere a little bit to the right of 0, and drew a tangent line, which is coinciding with the line itself, it's a slope of 0. So that's our right-hand derivative. Our right-hand derivative is 0. Now let's do the left-hand derivative. Any questions before I start that? Or anything you guys didn't catch because maybe the video froze? Nope, okay. So now, I'm going to go ahead and clear my drawings. For my LHD, the limit as h approaches 0 from the left side of f of 0 plus h minus f of 0 all over h. Okay. Well, f of 0 is still 1. That doesn't change. But now h is negative, right? H is negative because h is approaching 0 from the left side. So h could be like, say, negative 0.001. So you do f of 0 plus h, you're doing, again, h is negative. So you're doing like, like f of negative 0.001. Well, x is less than 0 now. So now you got to plug it into the other part, which was negative 1. So now you got negative 1 minus 1 over h. Well, that's negative 2 over h. Now, yes, you could plug in 0, you get something that's undefined. But again, h is not 0. H is a small negative number. So it's kind of like saying -2 or -0.01. Well, if I do that, that's like -2,000, I think. No, +2,000, my bad, because you're dividing two negatives. In fact, if I were to make a little table and plug in like, -0.1, -0.01, -0.001, if I were to do all that, I would get like, 20 and 200 and 2,000. So as h gets closer and closer to 0 from the left side, what's happening to y? It's going up forever. There's no limit to it, no bound. So we say this is actually going to be positive infinity. Or we can say it does not exist, because I don't know what that limit is. I don't know what that number is. It just keeps going up forever without boundary. So if my RHD earlier on was 0, but my LHD is positive infinity, or we can say does not exist, clearly my RHD does not equal my LHD. They don't equal each other. It's very, very clear that they do not equal each other. And so therefore derivative won't exist at x equals 0, because I found my LHD and RHD to be different. So ask questions before I move on to page 2, because I'm going to kind of use this result to help explain page 2. Are we okay? All right.
Mr. Ramashni.
Okay.
So what is the conclusion that we draw from LH and RH not being equal?
Not differentiable. You're not able to find the derivative x equals 0.
Oh, okay.
Because that's the definition of differentiability. The definition of excuse me, say it really fast. The definition of differentiability is that if the LHD and RHD equal each other, you are differentiable. If not, then you're not differential. You're not able to take the derivative. Let's look graphically.
Okay, thank you.
No problem. So let's look at the graph one more time here. Actually, that was included here. See, for the left-hand derivative, I was using f of 0, which is right there, and f of 0 plus h is like over here somewhere. If I try connecting those two, what's happening to that slope? That's a steep slope. And that slope only gets steeper, as we saw numerically over here. Now we're making that graphical and numerical connection, right? And algebraically is what's happening all over here. So it's all intertwined, right? And now we start realizing, okay, that left-hand derivative is definitely getting bigger, whereas that right-hand derivative is always at 0. Right? It's always right there. And so the derivative can't exist. So we can look at from a graphical perspective as well. So we now have deduced, because it was pretty clear that our graph was not continuous for this piecewise function, right? Yes, f of 0 existed, but the limit did not exist. It was in fact a jump discontinuity there. So what we've kind of deduced is that if a function is not continuous, then and let me actually expand that a bit more. At x equals a, so at some particular x value, then it's not differentiable also at x equals a. So a in this case was 0. At x equals 0, it was clearly not continuous, that we saw from the graph to this, right? And we just went through this formal process of derivatives, left and right derivatives, show they're not the same. So we can make that conclusion. That is stated on the second page, in the second box. If f is not continuous, let me position it this way. If f is not continuous at x equals a, I'm just repeating myself, then f is not differentiable at x equals a. We just proved that. Now let's do some logic here. And the way I'm going to go about this logic, let me go down to the bottom half of page 2, and I'll scroll back up to the top of page 2. Let's use a little logic to make sense of this statement in the first box up above. But I don't want to address that just yet. I want to do a little bit of logic with you guys. So let's say we have a statement, which I know is a true statement, and we'll use my name. And this is D period, of course. So if you're a student in my D period AP Calculus class, are you a student at SIGAR Prep? That's true, you are. Everyone in this Zoom class, Zoom meeting, is a SIGAR Prep student. You are registered. You know, you paid the money. You're a student here.
I'm a Menlo spy.
No, you're not. So now, what if I kind of mess around with this statement a little bit? The converse, and by the way, let's call this first statement here, let's call this P, and let's call this Q. So we say that P leads to Q. So where P is, does that lead to Q? If you're a student in my AP Calculus class, does that lead to you being a SIGAR Prep student? Absolutely does. The converse is when you do that. So what if I said, if SHP students then AP Calc, AB. Well, don't we have freshmen at the school who are SIGAR Prep students? Are they taking AP Calculus? No. So that's not true. So the converse is not necessarily true. What if I did the inverse is when you do negative P, so you negate. You keep the same order, but you negate. So what if I said, if no AP Calc, AB, then no SHP? Well, there are a lot of people who don't take AP Calculus AB. For example, my son is about to turn 4. He doesn't take AP Calculus AB. Well, actually, never mind. That made no sense. Sorry. That's the next one. Sorry. My apologies. Freshmen. Freshmen are non-AP Calculus AB, but they're still students at SIGAR Prep, right? Or what if you, what if you have a classmate like another senior who's doing like pre-calculus or AP Stats and not taking this class? They're still students at SIGAR, so that's not necessarily true either. However, what is true is a contrapositive statement. The contrapositive statement is when you reverse and negate. So negative Q leads to negative P. That's logically equivalent to the original statement. So the contrapositive of this would be, if not an SHP student, then no AP Calculus AB. With Mr. E. D period class. Now I could use my son as an example. He's almost 4. He's not a SIGAR Prep student. He goes to preschool. He's definitely not an AP Calculus AB. That's for sure. My wife graduated from here like what, 98, I think. So she's not an SHP student anymore. She's not taking AP Calculus AB with me. So, or anyone who's at Menlo or Burlingame, like Ian, as a spy. Just kidding. Again, that's a true statement. So with that logic, we can now make sense of the statement up above. So again, we said earlier, if not continuous, then F is not differentiable at x equals a. So if this were like negative Q and just like negative P, then P should lead to Q. So if I reverse those and say the opposite, if you have a derivative, you are continuous. So if something is differentiable at a certain point, it will be continuous there as well. So that's something that, so basically differentiability leads to continuity, but not necessarily the other way around, which we'll see in just a little bit. And obviously, if you're not continuous, as you saw here, then you don't have a derivative. Why? Because of logic. Because of logic, and of course, example 1 above. Because example 1 proved that to us. We did example 1 just a few minutes ago. Again, the left hand, right hand derivatives didn't equal each other. We knew initially that was not continuous from the graph. So if it was not continuous, we proved there's no derivative. Logically, if you reverse the statement and do this to the opposite, so then if you are differentiable, you are continuous, that makes sense. So
sorry, what's the difference between inverse and contrapositive?
Inverse is you simply negate each statement. You say the opposite.
Okay.
So for example, if I said, if it's Sunday morning, then I'll watch football. Okay. So the inverse would be, if it's not Sunday morning, then I won't watch football. So I just negate it. That's inverse.
Okay.
Converse is if I said, if it's Sunday, I will watch football. And then of course, or sorry, if I watch football, then it's Sunday. I meant to say that. Sorry, that's a converse.
Oh, okay.
The contrapositive would be you have to flip and negate.
Oh, okay.
Yeah. And the contrapositive is always logically equivalent.
Thank you.
By the way, for those who are too late for the ACT, because that had already happened, sometimes they ask this contrapositive statements. If anyone's doing the subject test, which I highly doubt, because I'm sure people are just going to do this next week and that's that. But if you found a place, sometimes they ask this too about like which statement's logically equivalent to this original statement. The contrapositive is always logically equivalent. Now let's look at this stuff here really quickly. Then we'll do a little homework review. So let's think about this statement here. If f is continuous at x equals a, so what if you're told you're continuous? Are you differentiable? F may or may not be differentiable at x equals a. For example, let's look at this point right here. Am I continuous there? Check. Am I differentiable there? I'm pretty sure I'm differentiable there because I could, the derivative is just going to be the slope of that line. Sure, check. Let's look at B now. Am I continuous there? Check. Am I differential at B? No. No, because it's a corner. Corners are not differentiable. Why corners not differentiable? Because the left-hand derivative and right-hand derivative are two different values. The left-hand derivative B I know is positive because that's a positive slope here. The right-hand derivative is negative, I know, because it's a negative slope. So what this tells me is that continuity does not guarantee differentiability. Just because you're continuous, whoop-de-doo. Tells us nothing about being differentiable there. I did know if you're not continuous, you're not differentiable. We just proved that about 15, 20 minutes ago. But if you're continuous, fine, but it still doesn't tell me anything about differentiability. And that right there was the converse of the statement on the top of that page. If you're differentiable, you're continuous. The converse is not necessarily true here. What about the inverse? If you don't have a derivative, f may or may not be continuous, depends. Just because you don't have derivative doesn't mean we can make a statement about the continuity. I'm not really sure. So let's take a look at this diagram again. So at B here, we're not differentiable, but we were continuous. At C here, we're not differentiable, and we're also not continuous. And we had proven when you have this kind of jump discontinuity situation in example 1, the left right hand derivatives are not the same. So that's the other issue too, is that a lack of differentiability tells us nothing about continuity. Tells us nothing about it. So the bottom line is this: continuity is needed for differentiability. You definitely need to be continuous to be differentiable. Because you're not continuous, you're not differentiable. We know that. But continuity does not guarantee differentiability, as you saw right here. Does not guarantee differentiability. So yes, in order for something to be differentiable, if you're differentiable, you're going to be continuous. We definitely need that continuity to happen to be differentiable, but just the continuity alone can't tell us whether we're differentiable or not. We can't say that. So that's probably a great place to kind of leave things right now. It's 2:50, so we're going to start doing homework in just a little bit. So I'm going to do a video kind of recapping what we just talked about. I'll probably talk about logical statements again, kind of recapping this. Then we'll do an example in the video where I'll have another piecewise function. We'll determine if this is differentiable at x equals 1. We'll do the left right hand derivative stuff again. And again, if we're differentiable, then we're continuous. We know this. But we'll kind of go through that. And then we're going to classify different ways you'd not be differentiable. Like this is when you have a discontinuity, when you have a corner. By the way, we call this a cusp. This is called a vertical tangent. I'm going to discuss all those different ways and what has to happen for these different ways of lack of differentiability to occur. We'll actually do an example of that. And that's kind of where I'll stop the video. So when we meet on Monday, I'll definitely pick things up from over here. And of course, recap what the video is about, because that's always good to do. So make sure you have your calculator ready. If anyone needs a calculator, let me know. I'm more than happy to leave some in the lockers at McGain. You can always pick them up if you don't have one. I mean, we got a bunch sitting here collecting dust. Just give them back to me at the end of the semester if you need to borrow one. But we'll kind of do a little calculator demo live on Monday. And we'll probably, my guess is, get to the end of page 7. And then the alternative definition of a derivative, as well as the intermediate value theorem. There's an IVT for derivatives also. I'll probably do that as a video that will be due for Wednesday at homework. Talk about that, and then we'll start 3.3 on Wednesday. So that's kind of how I'm kind of mapping things out here. I think that's all I really need to say that. Oh yeah, really quickly, there was some homework that kind of had this, so I'll go over that if you guys have any questions. So let me stop the video.